This is how deterministic chaos is totally different from physics intuition. Because in physics, we tend to think that when we have a small perturbation, this map and a map that's changed by 10 to the minus 16 in its height, all measurable effects should change very small. We have perturbation theory, everything is supposed to be smooth, etc. This is totally wrong in deterministic dynamics of chaos. Because what happens is, once you change your parameter by a little epsilon, you either end up in this interval or you don't. And why is that happening? In deterministic dynamics, we're allowing ourselves to go for infinite time. We're allowing ourselves to go very, very long time. In a very long time, what you think are small effects as a physicist, because I perturb my initial map, they end up in a huge effect. And the huge effect is that the dynamics is so discontinuous. I will show you in a second course that if you count the number of orbits, so this is in the future. If you put here the parameter of the map, for unimodal map by your stretching, and for Dike map by your stretching, and for Dike map is just where you cut the Dike map off. If you vary that continuously, and here you count the rate of increase of number of orbits, so this is called topological entropy, as a function of your parameter, parameter of the map. And this is how the number of orbits increases as you go one step forward in time. I'll define it later, but it's not very important. You'll discover that there is a regime when this map is so low that nothing happens. You have just one fixed point, so nothing is happening. There is a regime here where everything is possible. So this goes from 0 to logarithm of 2. Per step, the rate of number of increase of orbits is logarithm of 2. And now as you change this parameter, you will find that it's going to look like Devil's staircase. So it'll be a function that's monotone but no place differentiable. And one example I've showed you, one step is this step 3 orbit. Happens to be the thickest step. So there's a step here where I change my parameter, but nothing changes because the only thing that changes is the size of this basin of attraction. Topologically, I have this basin of attraction is complement. So in the Dike map, as I go through this interval, nothing changes in number of orbits. It's just the partition, a little bit. They squeeze more or less by the interval of attracting orbit, and that gives you a step. And the moment you understand it, you will understand, every periodic orbit will have a step associated with it, not just a 3 cycle, because you'll be able to adjust any periodic orbit to come close to the critical point. In physics, we expect that as I change my parameter, whatever I'm measuring should look something like that, and there'll be some perturbation theory that'll say it goes. Not so in determinism. In deterministic chaos, what you think is a family of dynamical systems are very different dynamical systems. They're discontinuous. So it's a curve that's no place differentiable. And that's the way the chaos works. It cannot be helped.